Okay. In today's video, we will consider line integrals of the second kind. Well, better, of course, line integrals of vector-valued functions. Okay, our concern will be functions of two variables into R2 again. So functions R2 into R2. Sometimes this is called line integrals of the second kind. Okay. Well, the idea was the following. Let us recall. Okay. The integral over a curve of a function, well, let me use here the f, ds was defined as the limit of, okay, we took a partition of C, so we had points, PIs, okay, and we multiplied this with PI minus 1 in length, which we showed as delta S, the arc length distance. Now, in this definition, of course, okay, why not replace ds with delta x or delta y? Well, of course, it can be done. A good question would be, why should we do it? But as we proceed in our examples, this will be clearer. Well, of course, we can. Okay. And, very importantly, okay, this is much more meaningful as we will see, than just being a curiosity. Okay. That's to say, let us define integral over C of fxy dx okay, is defined. I'm writing the shorter way, but the formal definition is exactly similar. Okay, so limit of the sum of f of pi stars, which I can consider as a point in the arc. Okay. Pi minus 1 pi, okay, where I will consider pi's as xi, yi in general. Okay, thinking this as a partition. Now, here we multiplied in the previous case this with the distance between pi minus 1 and pi. Here I will just take the distance between xi's, so that this more looks like a definite integral, but it's not a definite integral, as we will see. And this is the definition. This would be the limit of the Riemann sums, f of pi stars, this time multiplied with y differences. Well, I will not go writing everything in detail, but obviously, because these are limits of Riemann sums again, okay, they obey the basic rules, like linearity, okay, monotonicity, or not monotonicity, let us be careful there, or decomposition. Okay, we will have a comment about monotonicity here. So having defined these strange-looking integrals, let us just observe the following. Okay, firstly, these are if they exist, okay, are not, okay, partial integrals. As in, okay, iterated integrals. Okay. What do I mean by this? Well, in iterated integrals, you remember that when we had an integral of this form, okay, we just took y as the variable and integrated, keeping x constant. Well, but here x is not constant, because xy is a point on the curve, and when this point changes, both x and y change. Okay, this is because, firstly, okay, the point P, okay, changes on C. So, for example, the other one is similar. In the integral fxy dx, okay, y is not constant. So you have to be careful there. Okay. Secondly, right. Secondly, well, let us look at the following picture. Maybe that will be easier to understand. Okay. Suppose I have a curve like this. Say this is the curve C. So I partition it. This is the point P0. This is the point P1. This is the point, say, P3. And I have such a partition. The last one is Pn. Now here, okay, when I look at P1 and P0, that's the first line segment. Remember, we define these as line segments in general. Okay, I have here x0, y0, say, and P1 is x1, y1. Okay, in the integral, where I have dx, okay, I have x1 minus x0, which of course, in this picture, okay, is positive. So that's fine. But if I look at P, well, somewhere, of course, I have P2. If I look at P2 and P3, wait a minute, something is wrong. Yes, of course, this is not positive. It's negative. So when I consider P2, likewise, and P3, okay, from here, if I look at x3 minus x2, it becomes positive in this picture. So what's happening? Well, in a definite integral, x changes from a to b in an increasing manner. Well, here on C, xi's are not increasing. So, okay, on C, xi's are not increasing. So, xi minus 1 is not greater than or equal to 0 for every I. Well, this of course affects the monotonicity, because if you increase the function values in the Riemann sum that we defined, it does not mean the Riemann sums get bigger, because delta x's can be negative or positive. You have no guarantee there. So the composition property does not hold. Okay. So similarly, we have, well, that is, okay. These are not increasing. And so it does not look like a definite integral or a partial integral, as we already remarked. Okay. Well, let us see some examples. Okay. Firstly, let us consider a simple one. So let us calculate integral c of xy dx, where c is the part of the ellipse x squared over 4 plus y squared over 9 is 1, from minus 2, 0 to 2, 0. Okay. Now, a very important point here, especially coming from this picture, is the following. We start partitioning C, but we can do it both ways. We can start from this point as well. Okay. If we start from this point, all the x's will have a negative sign multiplied by minus 1. Because, okay, if this were Pn minus 1, then the difference would be xn minus 1. But if you change the notation, call this P0 and put P1 here, then you will have xn minus 1 minus xn. So there will be a sign change. In other words, when we discuss line integrals where we have just dx or dy, okay, the orientation, the direction of the curve is important, which means that it must be given. So, okay. We will see it in examples as well. So, this would be so, and say it is directed counterclockwise. So what is the picture? The picture looks like the following. Okay, we have 3's here and 2's here. So it is an ellipse, which is rather long this way. Now this is point minus 2 and this is point 2. So we move counterclockwise from here up to here. So it goes like this. So this is, okay. Now to evaluate the integral, of course, we need a parametrization. Since it's a directed curve, the direction must be observed. That is, we must be consistent with the given direction. So let us go step by step. Now, a parametrization for C, of course, would be the following. We already came across this before. It's like a circle, okay? So cosine t sine t is a good starting point, but it's not enough. When you add the squares, you don't get 1. Okay. Well, you have a factor 4 there, so you have to put 2's and 3's, which means that if you divide your x by 2, if you square it and divide by 4 and do the same thing for the y value, well, yes, you will get 1 at the end. Well, again, t plays the role of the polar angle here. Okay, it starts from 0, increases, but we are not on the curve. So we will be on the curve when that angle is exactly pi in the first place. So t, that's the angle, should change from pi to 2 pi. Well, let us check for the orientation. Does this representation give the correct orientation? Because it may not. It depends. Okay? So, at pi, yes, we are at -2, 0, which is our starting point. Good. And when the angle increases, it's bigger than pi, we continue in the correct direction. So, okay, check that the orientation, okay, which means that is increasing t direction, okay, matches the given orientation. Okay. Because it may not give the same direction. Well, but it does here. Okay? So it's okay. Well, then we can compute our integral. Namely, we have here, well, simply xy. X was 2 cosine t. Y was 3 sine t. And here, of course, we have dx. Well, x being 2 cosine t, that would be -2 sine t dt. And t changed from pi to 2 pi. So this is the thing we get. Well, of course, what do we have here? We have -12 of cosine t sine t. Well, that is sine 2t up to a constant. And so sine 2t, well, we can calculate that actually. That's simple enough. So this would give us sine 2t over 2 integral pi to 2 pi dt. Is that so? No, we have another sine t. So let us be careful here. That's not true. That is, what is that? Well, we can directly integrate. That's easier than that. So it is sine squared t and cosine t. Cosine t is the derivative. So it is sine cube t over 3. Okay. We have dx, yes. And, of course, pi to 2 pi. So that gives us 0 at the end. Okay. Well, let us now emphasize that again. Okay, that's the important note. In f dx or f dy, okay, C must have a given orientation. Okay. Well, why again? Because in the limit, we have xi minus 1. If the orientation is changed, it will just be the negative. So everything will change. Okay. Well, to complete, and the chosen parametrization must match this orientation. Okay. So you should choose a parametrization which is correct for this orientation, because not all of them give the same one. Okay. To illustrate this a little bit in detail, let us consider now the second example. Now let C be the part of, let's say, unit circle in the first quadrant. Let us calculate well, yes, in the first quadrant, oriented, I have to say that, counterclockwise. Okay. Calculate the integral over C of xy dx. And dy. Okay, as in the previous case, okay, we have a unit circle, so C has the natural parametrization, cosine t, sine t. The sum of the squares is 1. It's the unit circle. And t, because we have the part in the first quadrant only, t playing the role of the polar angle, starts from 0, goes up to pi over 2. Okay. Now, is the orientation of this representation, that is, when t increases, are we in the correct direction? Well, yes, because here, okay, this being C, the direction of C is counterclockwise, so it is like this. Okay. And when t is 0, we are here, fine. And if t increases, the angle increases, we move on the circle in a counterclockwise direction, up to pi over 2, where we stop. So here, the direction matches of this parametrization, okay, matches the given one. The given one is counterclockwise, okay, and the direction of this parametrization is when t increases. So you go in the same direction, so it's okay. Now the rest is quite easy after this parametrization. Well, we have okay, xy, so cosine t, sine t, and dx, that would be minus sine t dt from 0 to pi over 2. But this is xy dx, of course, over c. Okay, as before, derivative of sine is cosine, so this would be minus sine cube of t over 3, 0 to pi over 2, so that would be minus 1/3, whereas xy dy would be 0 to pi over 2 cosine t sine t. Okay. Now here we have dy now, okay, which would be derivative of sine t. Okay. So we have cosine squared, okay, and its derivative is sine t just by its side. So it would be cosine cube t over 3, but the derivative is negative, so we have this. Of course, at pi over 2, you have 0, so it is this time plus 1/3. So the direction and matching of the direction is very important. Okay. Now, a notation. Well, firstly, if we have two line integrals where we have dx and dy, we can put them together usually. That is actually the idea. So first of all, we write sum f, okay, rather let me put p here, that's the more usual notation, plus another function dy as, okay, integral c pxy dx plus qxy dy. Okay, it's understood. We don't usually put parentheses. It's understood that, of course, we have parentheses, and we can separate them in this form, but this is the more usual way. So we combine them. Okay. Now, we can also write this in a vector notation form. Also, in vector notation, we can write p dx plus q dy over c as c, the vector pq, here p and q are as above, functions of x and y, dot product, okay, dx dy. So we are doing nothing, just playing. Well, at this point, let us consider, okay, I will not write the differential notation, but delta x, delta y, to understand what's happening in a better way. Okay, we can write this as okay, delta x over delta t, assuming they are functions of t, because after all, in the representation of c, we will write x and y as functions of t, and delta y over delta t times delta t, which is perfectly all right. We can furthermore, instead of this vector, put a unit vector. That's to say, I can put here delta x over delta t, delta y over delta t, divided by the square root of delta x over delta t squared plus delta y over delta t squared times delta x over delta t squared plus delta y over delta t squared delta t. So I did nothing so far. Well, of course, the idea is to pass to derivatives if delta t is small. So this is almost x prime t y prime p divided by this norm times, now instead of this, of course, I can write my delta S. Because delta S was nothing but this. It was, cancel delta t's, you would have delta x squared plus delta y squared under root. That was delta S directed. Now, this vector is a unit vector, but note the vector itself, forget the norm, it's the derivatives. So it's a tangent vector to the curve. So this is a tangent vector to C. Okay? It's in the direction of the tangent line drawn to the curve. But we divide it by the norm, so it's a unit tangent vector to C. Okay. Shown by n. Now, what is n? N is a unit vector which is parallel to the tangent line drawn to the curve at the point xy. So it's a function of xy at the same time. It's not a constant. It changes as xy changes. Okay. Now, in this new notation, we can then write our line integral as follows. So, p dx plus p dy can be written as, okay, the integral over C of the vector PQ dot the vector n, and the rest, that is our delta S, becomes ds. So this gives us a relation between the integrals of the first kind and the second kind. That is, instead of the function, the vector valued function, we take its dot product with the unit tangent vector, and then integrate as in the first case. However, okay, one should be careful about the following, which we already said about these. Okay, when we have dx and dy, C must be an oriented curve. The direction of C is important. It must be given beforehand. Well, where is it here? ds has nothing to do with orientation. It's the positive square root of something, something. Okay, and you have dt, t increases, so there is nothing negative here. But here we have it. Namely, n is a tangent vector, and this unit tangent vector is not showing positive components all the time. It can have negative components. It's changing all the time on the curve. When the curve changes its tangent, so it always changes its direction. So this, okay, is important. It must be in the direction of C. Actually, the given direction of C. Well, the given direction of C, of course, is not a fixed direction. When you move on C, okay, this direction has movement on C. It's moving on a curve, so its direction always changes. So this will be another standard notation. Okay. Usually, we write PQ as a function f. Okay. We have p dx plus q dy written as f dot n ds. So this would be our new notation for line integrals of the second type. Well, before we pass to examples, note that this argument is valid if we had 3 variables instead of 2. That's to say, okay, this can directly be generalized to functions of 3 variables, which will be, okay, p of x, y, z, q of x, y, z, and r of x, y, z. So if f is from R3 into R3, which is usually the case in physical functions in line integrals, because we live in a 3-dimensional universe. Okay. Now, with more examples on this. Okay, let us calculate the integral of x plus y dx, where c is the right half of the unit circle. Okay. Well, let us just start with some parameterizations. For example, let us have cosine t sine t, t starting from, well, this being the right half over here of the unit circle. Okay, t can change, being the angle, from minus pi over 2 to pi over 2. Okay, the calculation would then give us, okay, minus pi over 2 to pi over 2. Well, x plus y would be cosine t plus sine t, and dx, which would be minus sine t dt. Now here we have cosine t sine t, which is sine 2t. Okay, integral would be cosine 2t. I'm not considering constants. And cosine 2t between these values would be 0. In other words, okay, this cosine t sine t would give us 0 with a minus sign and minus sine squared t dt. Okay. This gives 0. So what remains is minus pi over 2 to pi over 2. of minus sine square t, well, minus sine squared t would be cosine 2t minus 1 over 2. And the integral would give us sine 2t over 4 minus t over 2 minus pi over 2 to pi over 2. Okay. Well, this 2t makes everything 0. So we only have here pi over 2 minus pi over 2. And so that would give us minus pi over 2. Hope I did it correctly. Well, different answer here. That should be dx, so it is correct. So it is correct. So it is right. Correct. And when you integrate, you have these things. Fine. So you end up with this. Now, another right. Another parametrization would be say cosine t, and okay, check it correctly. So that would be right, cosine t and minus sine t. Here t runs from minus pi over 2 to pi over 2. Let us check if we have the correct one. At minus pi over 2, okay, we have 0, 1. So we are at the top. And when t is 0, we have 1, 0 on the right side. And finally, at pi over 2, we are at 0, minus 1 at the downmost point. Well, with this parametrization, then I would be the integral of x plus y dx, so that would be cosine t minus sine t, okay, and dx minus sine t dt from minus pi over 2 up to pi over 2. Of course, as before, we have cosine t sine t product, okay, giving us integral as cosine 2t, and of course at pi, wait a minute, yes, cosine 2t at pi over 2 or minus pi over 2 has the same value, so it gives us 0 again. So this part gives 0. So we only have minus pi over 2 to pi over 2 of sine square t. Well, note that it's exactly the same as the top, but instead of sine square, we have minus sine square. So this happens to be pi over 2. Okay. Now, of course, the results are just oppositely signed. Okay. The point is, of course, that even though both parametrizations parameterize the curve C, okay, without orientation, in fact, okay, these parametrizations give C, all right, but in different orientations. Actually, in opposite orientation. Namely, the first one, that is cosine t, sine t, where t runs from minus pi over 2. Pi over 2 gives us this c, but when t, the angle, the polar angle, increases, it's for this one. On the other hand, the other one, which is cosine t minus sine t, t minus pi over 2 to pi over 2, gives us the same curve, all right, the same c, not the same c in this sense. When t is at minus pi over 2, okay, this would be 0, and this would be 1, so you would be here. And if you increase t, you move in this direction. Okay. So this example, okay, shows us that, okay, thus the two parametrizations, okay, give the same C, but, okay, as oriented C, they give different C's. Namely, if you consider these curves as oriented curves, they are not the same. They are different curves. So, of course, we have different results. Okay, so what was missing here, of course, is that we had an integral with dx, but the orientation of C was not given. So the problem was not well posed. So, since initially the direction of C was not given, okay, this question, okay, is not correctly given. So we needed the direction to be given from the start. Okay. Well, as a second example, let C be the parabola x is y squared. Okay? But from this point, which is 1, 1, up to this point, which is 4 minus 2. Okay. And in this direction. So, if this is our C, okay, then we have the following. A parametrization, well, what is the integral? I'll give you that. That's not that important, actually. So it's, yes, it is an I with the integral over C of x dx plus y dy. Okay, we want to calculate this integral. Now, of course, we need a parametrization for C. Okay, a natural one, is because x is a function of y, use y as the variable, and consider this as the graph of the function x is f of y. Well, if you look in the other direction, it's a parabola in that sense. So, okay, a trivial parametrization using x is a function of y, the roles of x and y are changed, okay, we get x, that is y squared, and y. And of course, y changed from the lower value to the upper value, that is -2 to 1. Okay. Clearly, this parametrization starts when y is -2 at this point and traces everything up to 1, 1. Well, however, we have one problem. That's to say, okay, this gives C, all right, but in opposite direction. Okay. Well, if you recall our formulation, that is, it gives -C. Because -C meant the same C, but with the opposite direction. Okay, it's a directed curve, and so with the opposite direction, we obtained -C. Well, what could we do in this situation? Well, there are two things we can do. Well, we can look for a parametrization for C directly, not use this one. Okay. Either, okay, find a parametrization, okay, for C, okay, giving the correct direction. So do not use this one. Or better, okay, use the theorem. Well, this theorem will be very useful, so we will prove it. The theorem says the following. Integral over C of p dx plus q dy is the same as minus C p dx plus q dy. Okay. In other words, if instead of C you integrate over minus C, you will just have the negative of the integral you are looking for. But then you can calculate the right side and get the left side. Okay. Well, a proof, which is quite nice and easy, can be done as follows. Let us consider, okay, C given as, okay, x of t, y of t, t from A to B. A very standard way, okay, in the correct direction, of course. And we suppose a correct parametrization is given for C. Then we know the following. We already remarked before that minus C is given as x of A plus B minus t, y of A plus B minus t, P A to B. This gave the same, okay, curve because A plus B minus t, when t changed from a to b traces the same interval, but in the opposite way. So it gives us minus c. Okay. So the integral over minus c of pxy, let me just take dx, dy part is similar. This would be, okay, integral of po a plus b minus t, sorry, x of course, and y of a plus b minus t, okay, because this is the parameterization, and dx. Well, dx is x prime a plus b minus t and minus dt. And t changed from a to b. Okay, this being the parameterization, the only change is at this point. Well, now let us change t to s. Say, put s a plus b minus t. Then we have po x of s, y of s, okay, x prime s, and minus dt is ds. Okay. Now, how do the limits change? When t is a, okay, you start with b and then go to a. In other words, this is the negative of the integral a to b of px of s, y of s, x prime s, ds. Well, but this is nothing but just replace s and t in the standard way. So it's the integral over c of p xy dx. So this proves the theorem. Well, similarly for y. Okay. So now, let us go back to our example. And calculate the integral now, namely, so back to the example. Okay. The example said that, okay, we consider this parabola, and the parameterization for minus c, okay, was y squared y, and y changed from minus 2 to 1. And so the integral, forget the integral over minus c, okay, would be p dx plus q dy. Actually, yes, we have x dx and y dy. Okay, well, this being a parameterization, y changed from minus 2 to 1. We have x, okay, dx, which is 2y dy, plus y, well, dy is dy. So this is the integral in question. Okay, so we can calculate that. That would be 2y to the 4th over 4 plus y squared over 2 minus 2 to 1. And the calculation shows that it would give us something. Well, so it gives us, okay. Well, this is, of course, 1 minus 10, so that's minus 9. But then, the integral over c of x dx plus y dy would be minus integral over minus c. So that would be 9. Okay.